For this section, diagonalization is probably, if I had to pick the most important topic in linear algebra, it might be this. The reason being is we want to take a matrix and find a diagonal form of it. Let me show you something that is typical in a differential equations course. We may have something like this. Now that translates, that system of equations translates to the following matrix equation. So here's a system of differential equations. Now, with this, if I could somehow change this matrix to a diagonal form, I would be able to solve this. Now, you might look and you might go, well, all this really is the following matrix: A, B, C, D, but then we have x1 prime, x2 prime. If I go and try to do anything, say I try to solve, well, let me just do as an example here. I think it might be easier. Suppose I try to do 2, 3, 4, 5, and I wanted to do it augmented with x1 prime, x2 prime. I just want to do an example to show you how difficult this is. Typically what you might do is you might do negative 2r1 plus r2, and that'll wipe out what's below it. Get a 3 here, x1 prime, and then you'll get a negative 1 here, x2 prime, but I have minus 2 x1 prime. Well, what you have here then is this negative 1 means that negative 1 times x2 equals x2 prime minus 2x1 prime. These are all functions of t. There's no way of solving something like this because I have too many unknown quantities in one equation. So the problem with trying to do row reduction to solve these is what happens on the right hand side. So instead, this is not going to work. It's not working for me. So instead, what we do is the following. We take this A, B, C, D, and you have your x1, x2, and that equals x1 prime, x2 prime, and you swap it for another matrix. And here's what you get. You get this matrix right here. If it's diagonalizable, I'll be able to put in its place a diagonal matrix as such. Unfortunately, there's some baggage that comes along with it. I'll get a matrix P that's attached to it and a matrix P inverse that is attached to it. And the other side is still x1 prime, x2 prime. To solve something like this, check this out. I'm going to multiply both sides by P inverse, and I'll get the following. What I'm going to do is put parentheses around this second part because it's important. And notice that I'll get something similar on the other side. Now the real trick is this. You know that the P matrix, these P matrices are square matrices. They're invertible, so they're definitely square. And so whenever I take a square matrix times a vector, I'm going to get a vector out. So what I'm going to do is I'm going to let y equal P inverse of x1, x2. The beauty of this is then I get the derivative vector is P inverse x1 prime, x2 prime. I simply take the derivative. P is a matrix of just numbers, so you can do that kind of stuff. It's not my intention to explain all this to you, but to show you why we do such a thing as we do. So anyways, this was an aside. Let me come back to this equation here. We will get then d1, 0, 0, d2. And by the way, the d1 and d2 are eigenvalues, in case you were wondering. Then I'll have y, and that'll equal y prime. And then when I multiply this out, let me show you what happens here. I'm going to break it down into the following. Y, I'll call them y1 and y2. And that'll equal y1 prime, y2 prime. Now when I do the multiplication, I'm going to get d1 y1, d2 y2 will equal y1 prime, y2 prime. So then what I end up with is a series of equations. d1 y1 equals y1 prime, d2 y2 equals y2 prime. These are extremely easy to solve in this situation here. Now if d was 0, then y1 prime would be 0. All that means is that y is a constant. So those are easy to solve for any of these where the d is 0. In cases where the d is not 0, we would have something like this. And then you can integrate both sides with respect to t. Oops, I'm getting ahead of myself. y1 prime over y1 dt. And as you can imagine, that's equal to the natural log. So I'm going to have, on the left, I'm going to get d1t plus a constant will equal ln absolute value of y1. Then I can solve that and get an answer like this. y1 will equal e to the dt, I think I put a d1, times some sort of a constant. So then you get your answers like that. So your y vector will look like this. We would have e, well, let me put the c in the front, e to the d1t, and I'll call it a c1 just to differentiate from the c2, e to the d2t. Now if the d1 or d2 is 0, then it still works out, so it's not a big deal. So that's dc2 times that. Well, remember that y was equal to p inverse x. So I can get x back by replacing y with it. So p inverse x will equal c1 e to the d1t and c2 e to the d2t. And then to get x back, I multiply through by p. So you can see I get the solution to it using this eigenvector, eigenvalue thing. So the whole point of inventing the eigenvalues was to be able to solve these types of systems. And you can imagine, let me come back here to where I was talking about that was not working. Imagine how useless or impossible it would be if this were a matrix of, say, 500 by 500. Something of that nature would be absolutely impossible. Everything that is done down here, finding the inverse of a matrix, finding the eigenvalues, all that stuff is so computational that it can all be programmed in a computer, and so the computer can do all of this for you and spit out the answer. This is how they're solved. So, with that in mind, let me go ahead and start this, what I consider perhaps a capstone section on diagonalization. Everything seems to come together in this one section. So let me come back here and I want you to consider a certain matrix. If I have a matrix A, and it's a diagonal matrix, say, so we're going to be doing a lot of diagonal stuff here. Algebraically, they have a lot of good properties as well. Like, for instance, a squared will equal the following. It'll be 2 squared, 3 squared, 4 squared on the main diagonal, and zeros everywhere else. So it'll still be diagonal even after you do this. In fact, if you take it to the k power, whatever that happens to be, as long as it's an integer, well, a whole number, you'll get 2 to the k, 0, 0, 0, 3 to the k, 0, 0, 0, 4 to the k. So you can see it's very advantageous to have a diagonal matrix. Now, we're not going to get these exactly like that. Here's the form. The form ours is going to take. Our diagonalization takes the form A equals P times D P inverse, where D is a diagonal matrix. Well, you can see up here, when you take powers of a diagonal, it's very simple to do. Check this out. When I take a to the second power, I'm going to get P D P inverse. I don't want you to think this is the same a that I was working with just a minute ago. This is the format we will be working with here. But when I take a squared, I'm going to get this times itself. Well, you know, the associativity rules and all that will allow me to rewrite it this way. PD, and I'll put my P inverse P in parentheses, dP inverse. Notice what happens to the P inverse P. P inverse P is equal to the identity matrix. Of course, the identity matrix doesn't do anything, so I'm going to get P. I'll get D squared in the middle. DID is D squared, P inverse. So look, A squared, when I square it, A starts off as PD P inverse. A squared simply puts a square on the diagonal part. The other ones didn't even come into play. In fact, if you try to do a to the k, you get PD P inverse times PD P inverse times, and you would do that k times. But just like above here, between any two products, I'm going to get something like this. PD P inverse P, D, P inverse P, D, P inverse P, D. And this is just going to go on and on and on until I get to the last P inverse P, D, P inverse. And all those P inverse P's will cancel each other out, and you'll simply be left with P, D to the K, P inverse. Try it with some higher powers like 3 and 4 and see if you're not convinced this is true. But because all these P inverse P's cancel out, this happens. So algebraically, being able to diagonalize matrices is very useful as well. And you saw, coming back to what I just did with the differential equations, right here, once you get it in this format here, you're immediately able to read off the answers. So having a diagonal matrix in that spot is beautiful. You'll be able to read your answers easily. You'll be able to get a computer to pick off those answers easily as well. Now, I don't know where it took me, but here we go. This leads me to a definition. a square matrix is diagonalizable that's the word I'm trying to define, if there exists square matrices P and D with A equals P dP inverse, and D is also diagonal. So this is what we'll mean to be able to get something diagonalized, what I was talking about earlier. And so let's see what it is we need for this to happen. So we have a theorem. Start with let A be an n by n matrix. Then A is diagonalizable if and only if A has n linearly independent eigenvectors. So I've talked about the if and only if before. There's two parts to this. What we do when we do the proof is we go in two directions, they call it. Here's what I mean. So when I put my arrow like this, I'm going to assume the first part of it, which is we will assume that A is diagonalizable. So there exists square matrices P and D with D diagonal and A equals P D P inverse. Now what I want to show is that we get n linearly independent eigenvectors from A. So let's do this then. Let me write P equals V1, V2, up to Vn. We've done this before. I'm imagining that P is an n by n matrix, and it has n columns of these vectors. Each of these vectors is 1 by n in size. D, what I'm going to do with D is let that equal lambda 1, lambda 2, lambda n, but everywhere else it's 0. So it just has entries on the diagonal. Remember, some of these lambdas, I know I haven't mentioned them as being eigenvalues yet, but some of these lambdas are in fact, could in fact be 0, so keep that in mind. Now, let's go ahead and take a look at A times P. So whatever A is, I'm not really sure, but I'll put it here and let me replace P with these vectors. Of course, one of the things that you should remember is when you multiply this, here's the result that I get. I'll get AV1 will be the first column, AV2 will be the second column, and then AVN will be the last column. Now, on the other hand, I want to do P times the diagonal matrix. So we have V1, V2, Vn, times lambda 1, lambda 2, lambda n, but zeros elsewhere. When I multiply it through, I'm going to get the following. I think you need to keep this in mind. This is an n by n matrix. This is an n by n matrix. When I do the multiplication, I'll get n by n. But basically, here's what I end up with. I'll have lambda v1, lambda v2, sorry, lambda 1 v1, lambda 2 v2, lambda n vn. So, since A equals P d P inverse, let me multiply on the right by P. I get AP equals PD. So, this thing that has, these things that have the checks are equal to each other because they're the same thing, because of the assumption we're making here. Since A equals PD P inverse, AP equals PD. So the AP was this part up here. Let me write that in here. And that's equal to lambda 1 v1, lambda 2 v2, dot, 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 lambda n vn. Now, we should make it a point, come back here for just a second before I go further. These vectors here were vectors that made up the matrix P. P is invertible, so that means none of these vectors are zero. We do not, so they could be eigenvectors if we want. From this equation here, we can match columns with columns. So I get A v1 will equal lambda 1 v1, A v2 will equal lambda 2 v2, etc. A vn will equal lambda n vn. And what does it tell you? Since this means then that v1, v2, up to vn are eigenvectors by definition. None of them are zero, as I mentioned, because of that invertible matrix. And this is the definition of what we need for an eigenvalue, or an eigenvector eigenvalue combo. So why do we know they're n-linearly independent? Because since P equals v1, v2, up to vn is invertible, the column vectors are linearly independent. So this satisfies the proof of the forward direction. Now the reverse direction, this time I'm going to assume that A has n linearly independent eigenvectors. So let the eigenvectors be v1, v2, up to vn. Now, carefully here, watch what I'm going to do. I'm going to make the matrix P, but the vectors I'm assuming are ordered from 1 to n. So I'm going to put the first vector first as the first column, the second vector as the second column, and the nth vector as the nth column. Furthermore, let lambda sub I be an eigenvalue corresponding to vi. So then create a diagonal matrix D by, so all I'm going to do is take D, and I'm going to take my eigenvalues in order. Lambda 1 is associated with V1, lambda 2 is associated with V2, etc. Lambda n is associated with Vn, and I'll put zeros everywhere else. So when I do P times D, that we did this in the before part, we saw what we're going to get here. We're going to get a matrix, n by n matrix, lambda 1 V1, lambda 2 V2, lambda n Vn. All right, now notice that each of these, V1 being an eigenvector, means that it equals A times V1. Same with V2, that equals A times V2, dot, 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 that equals A times Vn. This is because A Vi equals lambda I Vi by definition of an eigenvalue eigenvector. All right, so then I can break this up into A times V1, V2, Vn. And so what did I have there? Let me see. This stuff over here, this is PD. So let me copy it down a few places. PD, PD, A, I'll replace this thing with P. And then I can multiply both sides by P inverse. I don't remember if I mentioned it, but P is the matrix of eigenvectors. This matrix is invertible. P is invertible because its columns are linearly independent. So anyways, as I go on, I was working towards that, and I got to the thing was diagonalizable. So the theorem is proven. Some of the things that you want to take away from this. Notice that P is a matrix of eigenvectors. And that D was a matrix of eigenvalues. But it was not only that, it's a diagonal matrix. What's important is that you should realize that when we made up A equals PDP inverse, when we do this, keep in mind the lambda 1 is associated with V1. Lambda 2 is associated with V2. So it's important that you put whatever vector you put here, its associated eigenvalue should be in that spot for the D matrix. For the second column, if you're going to use vector 2 for the second column, then you need lambda 2 to be in the second column of the diagonal matrix, etc. So you've got to match the columns of these two matrices up. So it actually tells you how to construct this. If we can find our eigenvalues, we can find eigenvectors, and then we can construct the matrix P of the eigenvectors, and we can construct the matrix D of eigenvalues. And that's what we're looking to do. So let's just look at an example. Here's the way they're usually described. Diagonalize. And they'll give you the matrix. Here I have A equals 5, 5, and then I'll put 1 and 0 in the other places. Now here you're like, this is very simple. It's almost diagonal as it already is. Well, the eigenvalues for or an upper triangular matrix, some people call it upper diagonal, I think I have before as well, we have lambda equals 5 and lambda equals 5. We have two eigenvalues, but they're the same value. Multiplicity is 2. So we already know how to find these things. Now, if I do A minus lambda I, that's going to equal 5 minus 5 is 0, 1, 5 minus 5. Something like this. So then if I want to find the null space, so we want to find the null space of A minus lambda I, we usually solve a matrix like this. Augmented matrix. Here, you see that X is free, but in the first row here, this is the Y value, Y equals 0. So your eigenspace, well, I should put it this way, an eigenvector equals the span, should I say span? No, I think what I'll do is, since X is free and the second component is 0, is going to look like this. But there's a much simpler way to describe that. I can pick any number I want to be a generator for these matrices. And so this is where I'll be using the span. We could have it generated just by the single vector 1, 0. So we would have then only one eigenvector. I need two eigenvectors. We need two linearly independent eigenvectors, but we only have one. So the matrix is not diagonalizable. It's a shame. It would seem like it is just because it's so close to being diagonal, but the fact is that is not the case. If you try as you might. Now you could I don't know if you can use row operations, but you could probably take this 5 and erase the 1, take 1/5 of row 2 and then negative row 2 plus row 1 would 0 that out, and you'll get a diagonal matrix in terms of row operations. So you're able to solve this thing, and the determinant's not 0. So you can find a unique solution. However, you won't be able to diagonalize it in the way that we're looking to diagonalize things. This time, our matrix will look like this. A will be 2, 3, 4, 1. So we're going to go through the process of finding the eigenvalues and breaking them down and everything like this. So first step was to compute this determinant. I'll call this the solution so you know where that's starting. The first step is to compute or set equal this determinant. 2 minus lambda, 3, 4, 1 minus lambda, and we set that equal to 0. Let me go ahead and multiply this through. 2 minus lambda times 1 minus lambda minus 12 is equal to 0. And then we FOIL this out and solve it. It's going to be a quadratic equation. When I FOIL this out, I get 2 minus 3 lambda plus lambda squared minus 12. And so this is, I'm going to rewrite it as lambda squared minus 3 lambda minus 10. And that's nice because it factors, so I have lambda minus 5 times lambda plus 2 will equal 0. So my lambdas will be 5 and negative 2. So those are my eigenvalues. Let's start with the smaller one, lambda equals -2. So remember, what we're trying to do is find the null space of A minus lambda I. So let me put it this way. Compute the null space of A minus lambda I. This is what you do after you get your lambdas. So I'm going to be looking for this 2 minus lambda, 4, 3, 1 minus lambda, and I'll set it equal to the 0 vector because I'm trying to find the null space of that matrix. So anyways, let me continue. 2 minus -2 is 4, then I get a 3, 4, 3. Obviously, I can wipe out the second row by taking the negative of the first row and adding to the second one. So I don't really think I need to do much here. Let me just write this so you can see. I can wipe out the second row easily. Negative R1 plus R2 will make that happen. And what I'll get then is I'll get 4x plus 3y equals 0. So I can make either one of these the free variable if I want. I will solve it for x. X will equal -3/4 y. And typically, so you can get one eigenvector that you could get is if you let y equal 1, then x will equal -3/4. But you can actually come up with a nicer one like this. A nicer eigenvector is the following. Instead, I can let y be whatever I want. Remember, this is spanned by the various y values because y is considered a free variable here. So with that in mind, if I let y equal 4, or better yet, if I let y equal -4, x will equal +3. And so this is the eigenvector I want to use. I'm going to use, for my first lambda will be -2, and the vector associated with it, I like to use 3, -4 instead of -3/4 1. They just are nicer and are easier to work with if I actually have to multiply stuff out later on. So my other eigenvector was lambda equals 5. And for that, let's take our A matrix again. So I'm going to have 2 minus 5, 4, 3, 1 minus 5, and I'll set those equal to 0. I'll get -3, 4, and then I'll get 3, -4. And you can see here, I can divide the first, I can do 1/3 R1, 1/4 R2. And then I can simply do R1 plus R2. And we simply, for this one, we get -x plus y equals 0, which is the same as x equals y. So an easy eigenvector here if you let y equal 1, x will also equal 1. So 1, 1 for that eigenvector. So do I have enough? It's a 2 by 2 matrix. I need 2 eigenvectors. Lambda 2 equals 5 v2 equals 1, 1. So I have enough eigenvectors. I have 2 eigenvectors. Are they linearly independent? So my 2 eigenvectors let me remind you what they were. v1 was equal to 3, -4. v2 equals 1, 1. And so, are they linearly independent? You won't have to check this. I'm just doing this, but you won't have to check this. These eigenvectors will be linearly independent from each other. But just to prove that they are, we can look at the determinant of the matrix that is created by putting these as vectors. So if I compute this determinant, I get 3 times 1 minus negative 4 times 1. And so I'll get 3 plus 4, that will equal 7. And so it's not equal to 0. So they are. Answer to that is yes. And so here's how we construct it. My A, it's only a 2 by 2, so I need 2 eigenvectors. And then I want eigenvalues in order, lambda 1, lambda 2. And then B1, B2, inverse. So in our case here, the V1 was 3, negative 4. The V2 was 1, 1. Lambda 1 was negative 2. Lambda 2 was 5. 3, negative 4, 1, 1, inverse. So remember A, let me replace A with what it was equal to. That was 2, 3, 4, 1. Now, let me actually multiply it out just to check. I don't assume you'll do this, although, to be honest, when I do these checkings, if I don't do them by hand, I plug them into my calculator and let it do them. Your calculator can do these multiplications as well, too. So you should be able to check yourself on these if you have enough time to do so. Let me go ahead and multiply it all out. Let me first get the inverse of this matrix up here. We already know the determinant was equal to 7. So I'm going to, well, I'll tell you what. Let me put the matrix first, and then I'll multiply by 1/7 after the fact. Remember, the way this works for a 2 by 2 is we swap the diagonal terms, and then we negate the off-diagonal terms. Now let's multiply this all out and see what we get. So I'll start with just these two, and I'll leave that matrix there for a moment. So when I do these, I do 3, 1 is matched up with negative 2, 0. So as we were mentioning, I'm just going to get negative 2 times 3. And then for the second part here, I'm going to then 3 times 0, 1 times 5 will be 5. And then when I do this, I'll get 8. And then finally in the last spot, I'll get a 5 as well. All right, let me continue. Now, once again, negative 6, 5 matched up with 1, 4. I'll get negative 6 plus 20 will be 14. Then negative 6 times negative 1 will be positive 6. Plus 15 will be 21. 8 times 1 will be 8. Plus 20 will be 28. And then finally, 8 times negative 1 will be negative 8. Plus 15 will be 7. Of course, when you multiply by 1/7 on the outside, you divide every entry by 7. So I get 2, 3, 4, 1, which of course is the original A that we started with. So you can see it's quite clearly diagonalizable. We had enough, we had 2 linearly independent eigenvectors, so that's how we knew that it was going to be diagonalizable. So this time A is going to equal, it's going to be a 3 by 3, so there's going to be some work to do here. We have negative 7, 6, 12. We make that negative more prominent. Then we have negative 16, 13, 16. And then I have 4, negative 2, 1. So we're going to try to do that. Let's find the eigenvalues first. So step 1 is to find the eigenvalues. And that means to find the determinant of this matrix, where you subtract lambda from the diagonal elements. Now, when I'm going to do this determinant, I see no advantage to going any one row or any one column. So I think what I'm going to do is just go down the first column and see what happens. So let's go ahead and do that. So if I go down the first column, remember the first entry is considered a positive entry. So I get -7 minus lambda times, and when I work this, I eliminate the row and the column that it's in, and I'm left with 13 minus lambda, -2, 16, 1 minus lambda. And then, as I mentioned, these alternate in signs. The next one will be a negative. So going down the column, I'll go to the 6. And if I eliminate its row and its column, what's left? -16, 4, 16, 1 minus lambda, and then plus the 12, and eliminate its row and eliminate its column, and I'll get -16, 4, 13 minus lambda, -2. So let's go ahead and compute all these. Remember though, the whole thing is to set this equal to 0 so that you can solve for lambda. So I'll put my 0 over here, and let me go ahead and do my multiplications. So for this one here, I'll get -7 minus lambda times, and then I compute the determinant of each of these as you normally would. So I'll get 13 minus lambda times 1 minus lambda, minus the other diagonal. So since it's -32, the negative of that is +32. And then I have -6 times -16 times 1 minus lambda. And then we have -64. And then finally +12 times -16 times -2 is 32, minus 4 times 13 minus lambda. Now, is there some trick or something like this to multiply it out? No, it's just multiplying it out in a very painful and slow method where you FOIL everything that you can, distribute whatever else you need. So let's start with this up here. When I FOIL this piece out, I'll get 13 minus 14 lambda plus lambda squared plus 32 minus 6. I'll distribute inside of these brackets. So -16 plus 16 lambda minus 64. And then plus 12 times 32 minus 52 plus 4 lambda. Let me continue on. 0 equals -7 minus lambda. Inside of here, I'll clean up as much as I can. It looks like I'll get lambda squared minus 14 lambda plus 45 minus 6 times. In here, I have 16 lambda minus 80. And then for the last piece, I get plus 12 times 4 lambda minus 20. All right, let me continue on. And I'll just continue multiplying this whole thing out. So I'll start by multiplying -7 to everything inside of there, and let's see what happens. I won't need the brackets here. I'll take them out. I'll start with -7 times everything. So I'll get -7 lambda squared. -7 times -14 is positive 98. And then -7 times 45 is -315. Now let me go and then multiply the negative lambda through. So I got negative lambda cubed. Then I'll get plus 14 lambda. And then I'll get minus 45. That's plus 14 lambda squared. And I'll get minus 45 lambda. Now, then over here, I'm going to get negative 96 lambda plus 480. And then for this last piece, I'll get plus 48 lambda minus 144. 12 times 12 gave me that. So let me go ahead and collect all of my terms. The highest power I have is to the third power, so I'll put that out front. Now let me find all my lambda squareds. I have -7, I have 14, and that looks like it. So I'll have plus 7 lambda squared. Now for lambda itself, I've got a 98 lambda, a -45 lambda. So between the two of those, I'm at 53 lambda. Now minus 96 will be negative 53 minus 96 is 43. So I'm at negative 43 lambda plus 48 lambda. Looks like 5 lambda. And then for the number part, the constant, I'm going to get negative 315 plus 480 minus 144. So negative 315 plus the 480 is 165. 165 minus 144, I believe, is 21. So let me check my work. This right here, I don't know why I put a 12. That was negative 20. And so this is 240. Well, that changes things then. Let me go ahead and do that again. So I'll start again. Negative 315 plus 480 is 165. Minus 240 is negative 75. So this is actually negative 75. So this is equal to 0. How do you solve a cubic equation like this to the third power? We have no formula for it. So what I do, I want to show you this while we're here, so you can see what kind of resources are available to you. Check this out. I'm going to do something called GEO, and if I scroll down here, see that GeoGebra? Let me click on it. All I got to do then is click in here. Now there's a bunch of things you can do in here, but let me just go to start graphing. And what it does is it gives me a graphing calculator. You can see what's new and all that, but I really don't want that. What I want to do is put this in there as a function, but I'll have to use x's instead of lambda, of course. So let me start that. And it'll graph as you continue. Use the arrow keys to come back down to the base. And let me see what else I need. I got my x cubed, then I want 7x squared plus 5x minus 75. So just a real quick check to make sure that I put in plus 5x minus 75. It looks good to me. And then what you'll notice here is it's crossing at -3, or it looks like it is, and it's crossing at 5. You may remember from calculus that when it goes through the x-axis like that, that means the multiplicity of this 0 is equal to 1. But when you do this, when it bounces off like that, the multiplicity is an even number. So in our case, since we can't go higher than a multiplicity of 3, that means this must be of multiplicity 2. I'll show you how it actually works. So we've got a picture of this. Let me make a copy so that we can use this in our notes. So this thing has been graphed. Let me come over here, put it in here. Of course, hopefully you realize what it's doing outside of there. This thing here is coming down, it's going down, and I don't know where it goes, but it is down and then comes up eventually to that spot. So it's doing that, and then this, of course, goes down. You know that a cubic polynomial must have 3 zeros, and this looks like it has all 3 of them. But here's how you break it down. You might remember this. Once I know that, do I know that negative 3? How do I know that negative 3 is a 0? Well, look, negative 3 to the third plus 7 times negative 3 squared. I mean, it looks like negative 3 from the thing, but I don't know for sure. What if it's like negative 2.999? Like it's not exactly negative 3. Could happen. So I'm just going to check here to make sure it actually is a 0, because I don't trust the graph implicitly. So anyways, right here, this double negative makes that a positive 27. Then here, you have positive 63. Then I have negative 15 minus 75. And so 27 plus 63 is 90 minus 90. And in fact, that does equal 0, so that checks out. Once I know that it's a 0, I can do this. Do you remember this? Synthetic division. I list my coefficients here, negative 1, positive 7, positive 5, and negative 75. And the way this process works is the first thing I do is I drop the negative 1 down, and then I take negative 1 times negative 3, which gives me positive 3, and I insert it under the 7. And then what I do is I add. 7 plus 3 is 10. Now 10 times negative 3 is negative 30 that I put under here. Add to get negative 25. Finally, negative 25 times negative 3 is positive 75. This does more than confirms that negative 3 is a 0. Right there it is. 3 and negative 3 is in fact a 0, which is what we got up here. This thing here is the same as this. It tells us more, though. It tells us the rest of it. So what I have is negative lambda cubed plus 7 lambda squared plus 5 lambda minus 75. Since I know that negative 3 is a 0, I know that one factor is lambda plus 3. I know the rest of it here. These give me the coefficients for what's left over. So I have negative lambda squared from the negative 1, there it is, plus 10 lambda minus 25. Now all I need to do now is break down that quadratic there. If you don't mind, what I'm going to do there is this. I'm going to take a minus to the outside so that this second factor is more like the things that I'm used to factoring. And I can see then that the second piece does factor. I get lambda plus 3 times lambda minus 5 squared. So that's our original characteristic polynomial. Now it's broken down all the way. So what I have then is lambda equals negative 3, lambda equals 5, and 5 are eigenvalues. And not only that, we can see that the multiplicity of this first lambda is 1. The multiplicity of the second lambda is 2. So this here has multiplicity 1, and this here has multiplicity 2. So now that we have them, let's go and get our eigenvectors. So next, find the eigenvectors. So I'll start with lambda equals -3. And what we want to do is we want to find the null space of the matrix where I subtract off from the diagonals that lambda. So what I want to do is I want to write it in such a way that you can see where my lambdas are coming into play. So the original matrix had us, in the first thing, it had -7, 6, 12. Then it had -16, 13, 16. Then it had 4, -2, 1. And we're trying to find the null space when I subtract lambda from the main diagonal. So there's a +3, a +3, and a +3. So this is where we have the negative lambda is right here. Let's go ahead and work this. I'll get -4, 6, 12, 16, 16, 16, 4, -2, 4. Now, right now, I can't really tell what relationship I have among the three variables. If I consider this the x column, the y column, and the z column, I don't really know what the solutions are just yet. But I do know this. I am going to divide the first row by -4. So for that one, I'll get 1, -4, -1. And the rest of the matrix is unaffected. Now, my next thing is I'm going to wipe out everything under the first one, under in this column here. I'm going to leave the 1, but I'm going to get rid of the rest of the things. So I'll do -6r1 plus r2, and then -12r1 plus r3. So I know how that one will go. That's easy enough. Now what happens to the next thing? I did -6r1, so -6 times -4 is 24, plus 16 will be a 40. And then -6 times -1 is +6, minus 2 gives me a 4 into that spot there. Then I did -12, so -12 times -4 is +48, plus 16 is a 64. And then -12 times -2 is 24, plus 4 is 28. Each step I want to check myself, so I'm going to put, I noticed that I forgot the -16 here. So that changes this then to a +4, and that changes a few things here. Now when I do -6 times 4, I'll get -24, plus 16 will actually be -8, will go into that spot. And then if I do -12, -48 plus 16 will actually be -32. So I have to be careful. I, for some reason, didn't see the negative in front of the 16 when I rewrote this matrix down. All right, now for this part here, I'm going to use the second row to wipe out the first and the third rows, at least what I can in the first row. But I think what I'll do first is divide this one by, I think, 2. So let me do 1/2 R2. And then this here is a positive. But I'll tell you what, when you make a mistake, you really have to go hunting for it. Anyways, let me see what we get here. We get -2, and then I'll get actually -4 and 2. And then I have -32 and 28. So now what I can do is I can simply add R1 to R2. Let me also check this last row before I go on. So -12 times -1 is +12, plus 4 is actually 16 right there. All right, I think we're good right now. Now what I'm going to do is I'm simply going to add R2 to R1, and then I'm going to do -8R2 plus R3. So when I do that, I'll wipe out this entry here, but then I'll get a 1 here. And then when I do -8 times 4, I get positive 32, so that'll zero this out as desired. And then when I do -8 times, I'll get a 0 here as well. So, and then I think the last thing I'm going to do is I'm going to divide the second row by -2. I probably could have done it before, but I wasn't thinking about it then. If I change to equations, and then I get 2y minus z equals 0. Z is the free variable, clearly. So let me change these. X will equal -z, and y will equal 1/2 z. So can you think of a good z value to use to give us a pleasant looking eigenvector? So an eigenvector that I could use here, I think since I can choose anything I want for z, I'm going to allow z to equal 2. The reason why is it's going to make the y be a nice 1, and x will be -2. So that's no big deal. So I've got one eigenvector down. My lambda that was associated with this is lambda equals -3. So we'll call it lambda1, and we will call this v1. Keep track of them because I want to keep them ordered when I create the PDP inverse. Next, we had lambda equals 5 and 5, but I don't need it twice. And I'll be doing the same thing as before. Start with the original matrix, subtract off the lambda, and let's go ahead and work this and find more eigenvectors. Now I need 2 more eigenvectors. This matrix so far only has the 1 eigenvector. I hope I get 2 of them out of this process. Otherwise the whole thing is not diagonalizable. All right, let's see what we have here. I get -12, 6, 12, -16, 8, 16, 4, -2, -4. I think the first thing I'm going to do is row 2 actually looks like the most convenient for me, because I can take row 2 and wipe out row 1, and then I can take row 2 and wipe out row 3. Here's how I can do it. To wipe out row 1, or at least this entry here, the initial entry, I can do 2r2 plus r1, and I can do almost the same thing for r3, -2r2 plus r3. And what it does is it wipes out the entries above and below it, which is exactly what I wanted to do. And now let's see what else has happened. 2 times 8 is 16, but plus -16 will zero that out. and then 2 times negative 2 is negative 4. That'll zero that out. And then down here, negative 12, I cancel that. Negative 2 would make that negative 16, wipes that out. And then this right here, negative 2, positive 4 minus 4 is 0, so it wipes that out as well. So what I end up with is 6x plus 8y minus 2z equals 0. I'm going to divide it by 2 just to make it a little bit simpler. 3x plus 4y minus z equals 0. So now we have 2 free variables. If we choose to, we can use y and z for those 3 variables, so let me do that. So my x will equal 1/3 negative 4y plus z. This is going to give us 2 vectors because you can allow y to be a number and z be another number. So for example, I could do y equals 3 and z equals 0. And that will give me negative 4. I chose 3 instead of 1 because I want to avoid fractions. Now on the other hand, we could do y equals 0, but z equals 3. And if I do that, x will equal 1/3 negative 4 times 0 plus 3. I'll get x is equal to 1. So my eigenvector and eigenvector is the following. I should say eigenvectors because we do get 2 of them. In the first instance here, I get negative 4, 3, 0. And then over here, I get 1, 0, 3. So let's do this. Let's do lambda 2 equals 5. Let's call the first vector v2. Then we'll call lambda 3 equal to 5. And then this vector here we'll call v3. So then when I construct the breakdown, it's supposed to be P, D, P inverse. The P is a matrix whose columns are the eigenvectors. So let me get the eigenvectors. The first one that we were going to use was negative 2, 1, 2. And then for vectors 2 and 3, I'll go negative 4, 3, 0, 1, 0, 3. And this is A. And then I put the eigenvalues in. My first one was negative 3. There's lambda 1, there's lambda 2, and there's lambda 3. This is our diagonal matrix right there. And then I copy the matrix again, the P matrix that is. And here is the diagonalization of A. A lot of work. You can imagine that it gets worse and worse as the size grows bigger and bigger. But there you have it. There was a full-blown example to show you how the setup is. Remember, how do we want it? This matrix here, P, has the eigenvectors listed in order. D has the eigenvalues listed in order. Remember, negative 3 was associated with this first vector. This 5 was associated with the second vector. The 5s don't matter much because I could have associated either one with either vector. But the important thing is that you have v1, v2, v3, lambda 1, lambda 2, lambda 3. And then this is the same thing, it's just inverted then. Now, notice also this. I said we needed 3 eigenvalues completely. And so we had 3 linearly independent eigenvalues. You don't have to actually go and compute this determinant to see if it's invertible. It's going to be a given. It will be invertible. So there they are. You don't have independent eigenvalues. You have linearly independent eigenvectors. That's the key. If you have 3 linearly independent eigenvectors, then you know you're going to have a diagonalizable matrix.